Hey there and welcome. Today we are diving headfirst into that incredible 3-pound universe we all have inside our skulls. We're going to tackle a really fundamental question about how our brains actually work. For years and years, one idea, one metaphor has really dominated the conversation. But what if we've been missing a huge part of the story?
So let's just get right to it. Is your brain basically a biological computer? A tangle of wires and switches that are just processing ones and zeros? Or is it something more alive? Something more like a physical substance, where thoughts aren't just sparks, but actual ripples flowing through it, like waves in a pond? All right, let's jump in. First, we're going to look at the metaphor that's been the king of the hill for almost a century. And then we'll get to the new perspective that's starting to challenge it.
Okay, so this slide really lays it all out, side by side. On the left, you've got the classic computer idea. And look, it's been powerful, it's been useful, it's gotten us so far in understanding the brain. Neurons are the wires, and those little electrical spikes they send are the digital code. But then, look over on the right. This new way of thinking suggests that the brain's physical stuff, the actual tissue, is an active player in the game. Signals aren't just electrical sparks, they're physical waves, and the paths they take are less like fixed copper wires and more like riverbeds that can change over time.
This computer metaphor has been absolutely fantastic for mapping out neural pathways and figuring out how signals get from A to B. It gave us a structure, a way to even begin analyzing the brain's unbelievable complexity.
But, and this is the big but, here's the question that changes everything. Think about a regular computer. Its hardware, the silicon chip, is just a passive stage for the software to run on. What if the brain's hardware, all that soft, wet, squishy tissue, is actually part of the calculation itself? What if its physical nature literally shapes our thoughts?
And that question leads us to a completely new way of thinking, a framework that totally embraces these physical properties. It's called the Brain Kinematics Model.
So the Brain Kinematics Model, or BKM for short, says that when a neuron fires, it's not just an electrical event. It's also a mechanical one. It actually creates a tiny physical force, a little push and pull, or what engineers would call stress and strain, on all the tissue around it.
And the absolute core idea that comes from this, the one term to really remember, is neural strain flow. This is it. This is the central concept of the whole model. It's how we can imagine thoughts physically moving.
This is the perfect way to picture it. Imagine a thought not as a single spark jumping across a gap, but as a pebble being dropped into a pond. It creates a ripple, right? A wave of physical movement, of strain that travels through the water. In this new model, the brain tissue isn't just some passive bucket holding all the sparks. It is the pond. The medium itself is the message.
So if we're going to go with this idea, we kind of need a new way to talk about all the brain processes we already know about. And that's exactly what the BKM gives us, a whole new language.
Now, this is a really important point. This model is not trying to throw out decades of incredible neuroscience. Not at all. Think of it more like a new layer of understanding, almost like a Rosetta Stone that lets us translate concepts we know from the electrical world into the physical world. Okay, check out this table. It's pretty cool. What we've always called neural pathways, the BKM reimagines them as strain flow highways, like the main riverbeds where these physical forces prefer to travel. An action potential, that classic neuron spike? In this world, that's a strain package, a neat little bundle of physical force. And you know those big rhythmic brain waves you can see on an EEG? The BKM sees them as phase waves, which are just the large-scale combined motion of all that strain flowing through the brain tissue.
So what's the big deal about this new language? Well, what's so powerful is how it helps us connect the tiniest little events happening in the brain to the biggest, most complex patterns of our thoughts.
So, how does it all build up? Well, it starts super small, at the level of individual synapses passing these tiny physical strain packages back and forth. Then those little packages start traveling along the established strain highways, and they merge and flow together into bigger currents. And eventually, all these little flows synchronize into these massive brain-wide phase waves. And it's these giant waves that create what we see as our functional brain networks.
And that brings us to a huge idea in modern neuroscience, dynamic functional connectivity, or DFC. It's basically the observation that different parts of your brain team up in these constantly shifting groups to get things done. The BKM gives us a physical reason for this. It says these teams, these alliances, are formed by the ebb and flow of those massive physical phase waves that coordinate everything across the entire brain.
So we've got a new model and a whole new language. But what's the real test of any scientific model? It's got to make new predictions, right? Things you can actually go out and test in a lab.
And that's why this really matters. This isn't just some philosophical game of swapping words, thinking about the brain as a physical substance instead of just a circuit board. Well, it opens up entirely new experiments and lets us ask questions we never would have even thought of before. And here are 4 really big ones. First, imagine that the physical stiffness or softness of a brain region could act like a filter, either letting signals pass or blocking them. The model also predicts that our different cognitive states, like when you're super focused versus when you're daydreaming, are a direct result of these physical wave patterns. It even suggests we could one day influence major communication hubs in the brain just by physically tweaking them. These are real, exciting, testable ideas.
At the end of the day, the goal here is to create what the researchers who proposed all this call a single continuous narrative, a story that finally unites our understanding of the brain's electrical signals with its deep, fundamental physical nature.
It's honestly a pretty profound shift. We're moving away from the metaphor of a static, rigid machine, and we're moving toward a vision of the brain as a dynamic, living, and physically responsive substance.
And that just leaves us with this one last fascinating question to think about. Could the actual physical properties of your brain, its stiffness, its density, its literal feel, be just as important as its wiring diagram? Could the very shape of your consciousness be sculpted by the physical forces flowing through it? That is a whole new way to think about thinking itself. Thanks so much for joining me.